In today's video, we're going to introduce a number of tests for a series of positive terms. The most useful test of them all is the comparison test. So, we are going to study about comparison test. There are various ways of stating the tests. Statement A. This says, let summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms Now suppose summation n equals to 1 to infinity bn is known to be a convergent series. Okay, then if there exists a positive constant k and a positive integer n, such that an by bn is less or equal to k for all small n greater or equals to the positive integer capital N, then summation an also converges. Now this is a case for convergence. We must know that this symbol means there exists. Now we'll check statement B, which is a case for divergence. Let summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms, just like the previous one. Now suppose summation n equals to 1 to infinity bn is known to be a divergent series. So if there exists a positive constant say L and a positive integer capital N, such that an by bn is greater or equal to L for all small n greater or equal to the positive integer capital N, then the series summation an also diverges. Now this is a case for divergence. The next statement is statement C, which is for convergence. Now this is a more general form of the previous two statements, which is A and B. Here we are going to introduce upper and lower limits. So let summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms. Suppose summation n equals to 1 to infinity bn is known to be convergent. If now upper limit an by bn is positive and not infinite, that is 0 less than upper limit of an by bn less than infinity, then the series an is convergent. Similarly, we have a same statement for divergence, which is statement D. Similarly, we write let summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms. Now suppose summation n equals to 1 to infinity bn is known to be divergent. If now lower limit an by bn is greater than 0, then the series an diverges. This was the statement for divergence. Now the fifth statement, which is statement E, is the limit form of comparison test. Now this is a special case where limit an by bn equals to L, that is upper limit an by bn equals to lower limit an by bn equals to L. The statement is if summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms such that limit n tends to infinity an by bn exists and equals to L. Say where 0 is less than L less than infinity. Then either both the series, which is summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn, will converge, or both of them will diverge. This brings us to the sixth statement of comparison test, which is as follows. Statement if. If summation n equals to 1 to infinity an and summation n equals to 1 to infinity bn be two series of positive terms, and if there exists a positive integer small m such that an by an plus 1 is greater or equal to bn by bn plus 1 for all small n greater or equal to small m. Then there are two conditions, which is then number 1, the series an is convergent if the series bn is convergent, and number 2 is the series bn is divergent if the series an is divergent. Taking a look at a couple of simple examples, the first one is we are given this series summation n by 4n cube minus 2. We need to check whether it converges or diverges. So we'll take this as series an. Now we need to compare it with another series bn, which we will take as the series bn equals to, from here we can say n by n cube. This can be written as 1 by n square. Now we know that 1 by n square converges. We know this from P series. Now what does P series state? The P series states that summation n equals to 1 to infinity 1 by n to the power p converges if p is greater than 1 and diverges if p is less or equal to 1. So this is the P series. From this one we can say that 1 by n square converges. So comparing an with bn, we can say that the series an also converges. Now the second series is summation n equals to 1 to infinity 1 by root over n into 2n plus 1. We need to check whether it diverges or converges. So we will take this series as an. Comparing it with bn, where bn equals to, from here we can take 1 by root over n into n, which is 1 by n. So an by bn gives us an by bn tends to 1 by root 2 as n tends to infinity. So summation an and bn, that is the series an and bn, will converge or diverge together. But as we can see that the series bn diverges due to harmonic series, so the series an also diverges. As series bn diverges, hence the series an also diverges. The third example is, we are taking the series an as summation n equals to 1 to infinity an equals to 1 plus 2 by 2 cube plus 1 plus 2 plus 3 by 3 cube plus 1 plus 2 plus 3 plus 4 by 4 cube, and so on till 1 plus 2 plus 3 plus till n plus 1 by n plus 1 whole cube. This goes on. So we can write that an equals to 1 plus 2 plus 3 plus till n plus 1 by n plus 1 whole cube. This can be written as n plus 1 into n plus 2 by 2 into n plus 1 whole cube, which is equals to n plus 2 by 2 into n plus 1 whole cube. Now we need to take a series bn for this to compare it. So we are taking bn equals to, from here we say n by 2n square, a simple series which equals to 1 by 2n. Now comparing the series an and bn, we see that an by bn gives us n plus 2 by 2 into n plus 1 whole square, this will be square, by 1 by 2n, which equals to 1 plus 2 by n by 1 plus 1 by n whole square. This tends to 1 as n tends to infinity. Thus, limit n tends to infinity an by bn equals to 1, and the series n equals to 1 to infinity bn diverges. So therefore, the given series, which is summation n equals to 1 to infinity an, also diverges. So in this way the comparison test is done. Stay tuned for the next tests.